Welcome everybody to another video. Today we have another special guest reappearing, I think third time in recent memory, but I'm sure it's been more than that. But Asher, welcome back to our channel. Tell us what we're going to be looking at today.
So we're looking at a protein called Casein Kinase 2. So it's a kinase. We're all familiar with kinases. And I guess generally, if we speak about kinases, we're thinking about the context of metabolism, or thinking about the context of, well, what diseases are kinases going to target? Cancer. I mean, cancers, metabolic pathways often are going to be cancer targets. And the particular PDB file is an allosteric site. And as both of you guys know, I'm very interested in Allostery, and we talk about Allostery a lot. And you might ask, well, why is Allostery so cool and important? Well, because it's not a competitive inhibitor. It's not competing for a binding site, in this case with ATP. It's binding to a site near the ATP binding site, but it's actually disallowing the binding of ATP by changing the shape of the active site, not by directly competing with it. So it's interesting and cool in that it's not going to cause things like receptor desensitization, which you see with GPCRs a lot of the time, because you're not blocking that active site. This is a collaboration I picked up with a group in Germany. I saw an interesting crystal structure paper, as I usually do. I emailed the group and they said, sure, we're interested in SAR type work and discovering new ligands. So this is a project that I picked up about a month and a half ago, and I've been running the virtual screen. And what we're going to be looking at in VR are some of the compounds that are going to also bind to this allosteric site. Of course, a lot of this data is, of course, unpublished, and not that that's a big deal, but it's also unverified. We haven't purchased the compounds yet. There's always more computational work that needs to be done to selectively make our screen as small as possible, so we're not testing hundreds to hundreds of compounds. Ideally, we want to get to the testing down to maybe 30, 20 compounds that we think are definitely going to bind, and then test them that way.
Is ATP, so ATP is going to be in the binding pocket, and then we're kind of going to be looking at all the ligands in that allosteric.
Yeah, in this particular crystal structure, we're actually not going to see the ATP at all. It's actually not in the region of the protein that I'm looking at, but it is by definition an allosteric site of the protein. So we're not going to see the ATP actually, but just rather the allosteric modulator.
Okay, that's awesome. And have you already done some other like MD work that kind of see how it flexes the protein after the binding?
I'm actually, to be honest, I'm not there yet. I haven't done the MD on this yet. I usually prefer to do the MD after we have some hits.
Yep.
So probably like a few months from, I'm still running the screen, probably in 3 or 4 months when we get some data, after we purchase the compound, send them to Germany, get them tested by the collaborators, then we can do some MD to kind of see how the compounds actually are promoting inhibition via changing the active site.
Right. And which database did you say you used for this? Was this Inhibition Real or?
Oh, I usually use Zinc. That's kind of my go-to. So I go through Zinc, and then I filter through MolPort. I filter through MolPort's database to see which compounds you can buy. It's usually overkill to do it through Zinc. It's probably, if you're a synthetic person, then it's great to do it through Zinc, because then you can probably make half these compounds. But because I'm not a synthetic person, I'd rather just look through databases that the molecules are, you can buy them, right?
So you'll buy 20 to 30 of these, send them out to your collaborator, do a screen, and then maybe if you get a few hits, do a little bit of like medchem work, or like what?
Yeah,
this project.
I mean, I think in terms of like academia, you can go the route of finding hits, validate they bind, then you can, a lot of people that I work with do actual cryo-EM or X-ray, which is nice. So you can very well, not very quickly, I don't want it to mean the work, but you can essentially get a crystal structure. Then you can, based on the crystal structure and exactly what you said, you can do the SAR work on it to look for more potent inhibitors through allostery, is what I'll say.
Yeah, that's awesome. So it looks like we have maybe 30 or so compounds that we're going to be looking at today.
I think it might be quite a few. What I tried to do is I triage them via structural similarity, and I only picked compounds that have more negative docking scores than the actual co-crystallized ligand in this PDB file.
Great. So you're not looking at like biocompatibility or any other factors, right? Just
not yet. To be honest, usually for me it's super. My work is a lot focused on just finding molecules that bind. Whether or not when you put those into a biological system will they actually reach the biological target is unknown, right?
Yep. Yeah, they all seem to have very similar shapes, and they were all kind of like long. Yeah, not super long, like a
Well, when we go into VR, we'll actually see that the actual co-crystallized ligand is a large molecule.
Yeah. Okay. Awesome. Yeah, I'm
Yeah.
excited to hop in and check it out.
Me too. Let's do it. We're looking at a PDB file called the protein's casein kinase 2, as we were talking about, and we're discussing how normally this protein binds ATP, but we actually don't see the ATP because the ATP is not actually in this region of protein. What we're actually looking at is this is an allosteric site of casein kinase 2 protein. So as we were talking about, not in VR, how this basically works is this allosteric site will bind to this co-crystallized ligand, and it'll change the shape of the ATP binding site such that it won't bind as well, or it'll inhibit how well it binds. And essentially, you're looking at a way of turning the protein to a lower threshold by not allowing ATP to bind and get cleaved and transfer one of these phosphate groups. If we think about kinases and the way they function. So we're just basically looking for using high-throughput virtual screen to look for allosteric modulators with overall similar three-dimensional shapes to our allosteric modulator, but have different chemotypes, right? So they're different scaffolds in general, and that's how we find new molecules that bind to proteins. We want a similar overall three-dimensional shape, but in a two-dimensional sense, the actual structure two-dimensionally is vastly different from this structure over here inside the binding site.
That's awesome. And it sounds like we have a few hydrogen bonds that we've picked up with the co-crystallized ligand, which makes a lot of sense.
Yeah.
Because it's co-crystallized.
Yeah, so we should see some obviously side chain amino acid interactions with parts of the protein. So over here it looks like we have a histidine hydrogen bonding to a oxygen. This is sulfonamide, right? You see this a lot with antibacterials, actually, the sulfonamide groups, right? The SO type chemical bond, sulfonamides. And let's see what else we see here. We see this is a backbone hydrogen bond, which we're actually not too concerned with, but the more apparent one is the one with that histidine residue that we saw before, right over here, between the histidine and the sulfonamide O and the nitrogen, between the nitrogen, it looks like.
So before we get into some of the compounds that you screened, is there anything that you don't like about this co-crystallized ligand, or any particular areas where you think there might be maybe more space to build out, like instead of a chlorine, if you, I don't know, kind of built into the pocket or something on the other end?
I mean, what's super nice is we can actually see in VR, we have this really nice surface view, so we can kind of see if you look. I would say in this deeper region of the pocket over here, you're not that you're limited to smaller type things, but it does kind of close in pretty quick. But you can kind of think about this region over here that I'm pointing at is it's pretty open, right? It's pretty open, so you can sort of build things out. But if you go too far out, you're going to be sort of outside the allosteric site. I mean, in general, what I would say is it's a nice file. What I like about this crystal structure is the co-crystallized ligand. It's big. It's a large ligand, and that usually gives you a lot of space to work with when you're trying to design compounds. You're probably going to looking at compounds that are at or near 500 AMU, right? These are pretty big. These are hefty ligands. There's actually a lot of room to build overall in this PDB file.
Well, it's huge. I'm kind of wondering if we could, just chop off these two, 6-member rings, and you still kind of get the effect, or if kind of building into this particular pocket. Um, I'm just gonna call that traction down, down deep into that area. If that's kind
Right.
of necessary for activating the allostery.
Well, I think overall, I'd say probably, I don't know. I mean, probably, I'm actually not sure, to be honest. If you just chop off large parts of the region, would it still bind to this allosteric site? I can actually definitively tell you.
I'm not an expert medicinal chemist, but trying to make this into a drug, I'd be like, all right, let's just cut it in half, make it a bit smaller.
Yeah, yeah,
Yeah, this
yeah.
is awesome.
I mean, I would imagine I'd imagine, well, there's two sort of folds here. Like larger ligands are going to have a hard time getting right inside of this protein, but this particular protein not so much, because it's open in the backspace over here. But I think these bigger ligands would actually give you pretty good selectivity and pretty decent affinity, because they're larger. They're having more interactions with side chain amino acids. That's what I would imagine.
Yeah, definitely. Actually, there's a few side chains that maybe we could pick up some new interactions. Not saying that we need to do some medchem work today, but just to do some measurements with our measurement tool, just to kind of get a good idea of potential areas where there could be some more interactions if we were to do some modifications to the ligand, and kind of try to pick up some more interactions with the side chains. Those are the ones that I'm seeing. I guess maybe where this chlorine is, you could try to kind of make
Yeah.
interaction with that glutamine over there. Yeah, I mean, I'd say those are probably all the good potential ones that I see immediately.
Yeah, I mean, I was actually even thinking about I was thinking about a pi over here between this ring and this aromatic, like a T-shaped pi interaction is what I was thinking, but maybe not. That'd be, just in 3 dimensions. I wouldn't have noticed that in 2 dimensions, but in 3, you can kind of see it. You kind of think about maybe a T-shaped pi interaction there between these 2 rings, but just looking around for other possibilities here. 4 angstroms is pretty, for a pi. That's actually okay. For the
Yeah,
geometry
edges
is
of the
probably
carbon
not
closing.
exactly right, but yeah.
Yeah, I
But no,
mean,
that's
like
good.
this thing would have to kind of flip a bit.
Yeah, the geometry is
I don't. I
not
mean,
perfect,
there's
but it's
probably
just
some
the
states
thought.
where they interact a bit. Just maybe not in this co-crystallized
Yeah,
state. But if you ran MD, I wouldn't be surprised if these kind of line up and do a little bit of pi
yeah.
stacking.
You generally see pretty you can see pretty big movements with MD, as we all know. So yeah, for sure.
Yeah. Okay. Do you want to hop in and look at some of these other compounds that you screened?
Yeah, for sure. So I think what's apparent about what I noticed right away is the co-crystallized. This also has that aromatic group on right. It has this side, the aromatic group that we were kind of talking about, the co-crystallized ligands. The middle, I don't know. I actually like what you said before, Steve, about if I chop this molecule in half and this part fits in. You have a part that fits in this side of the protein and a part that fits in this side of the protein. You actually you can kind of imagine in a way, because the molecule does have to bend quite a bit to go into each pocket. It is almost like a 90-degree turn of this linker region right here, right between this part and this part. You're kind of at a 90-degree angle, aren't you? I never really thought about it that way, but you have to have a bit of a twisting motion to get into there.
Yeah. Yeah, but maybe it's kind of necessary to get some of the effects of that allosteric interaction.
It
But yeah,
probably
I'm also
is.
curious, like which one's kind of the more important region, if you only bound in this, I'm gonna call it the top half, versus if you
Mm,
only bound to the bottom half, would they have
mm.
the same effect, different effect, no effect? Do you need both? Yeah, a lot of what I assume are open, scientific questions, and this is great that we have researchers like you to kind of get to the bottom of that. Yeah. For the audience at home, yeah, these things are freely rotatable in 3 dimensions, and so this might be the bottom half for you and the top half for you. I just have it oriented so that this is my top. But yeah, there's basically kind of a mini pocket one and like a mini pocket two. And so, do they both have the same effect? Are they both necessary to form this sort of, mega allosteric cryptic pocket thing going on? Or do you just need one of them? I'd love to, dig deeper on that.
Can't promise there'll be any, but let's give it a go.
Yeah, it looks like we only picked up one. Just that one little hydrogen bond right there.
Yeah, and it's not even a side chain, so I'm not too concerned with it anyways. And like I said, I think that's because the way I modeled this, I actually left the waters in the bonding site when I did all the protein prep and minimization. And then when I docked everything, I took the waters out. That's usually what I like to do if there's waters in the binding site. For these type of kinases, yeah, you typically do see waters inside the binding site for most kinases.
Great. How about we overlay a few of them just to
Yeah,
kind
for
of get
sure.
a little bit of an overview. Just to get an idea. Yeah, I had all 29 of these overlaid, and that was a bit much, but maybe we could just do 5 of them here or so. You can see, yeah, the shape similarity. Yeah, these are all
Yeah.
very similar shapes here, and they all
Yeah,
docked in
I was
very similar poses.
I was looking for similar when I ran this screen and kind of put it together. I was looking for more of a thinking about SAR type thing. So overall, I was thinking about sort of similar shapes. But yeah, this ring on this dual fused ring system in the bottom is the same in most of those structures. If we kind of think about it, we're both looking at this bottom region right here.
Yeah, and of the 5 at this
And
sort of right angle junction, yeah, none of them have that sulfur piece like on the co-crystallized ligand.
Right, and they're all. And what's nice is they're all filling up the binding pocket. They're filling the whole binding pocket up pretty well, kind of like how the co-crystallized ligand was, which is nice, right? Which what does that ultimately mean? Well, that ultimately means that we have overall a similar 3-dimensional shape between our co-crystallized ligand and our research compounds, but structurally in 2 dimensions, they're quite different structurally.
Yeah, in particular, there's I think was it the yellow one? Yeah, this one. So I'm gonna turn on some interactions for this. I think it's this one. Perfect. Okay, yeah, I just wanted to show that we are picking up that one random hydrogen bond that I was saying, oh, it'd be nice if we could form a hydrogen bond with this oxygen here. So yeah, one of them does pick that up. Oh yeah, we picked that one up here.
Yeah, for sure.
This one also in this sort of mini pocket, down here, also doesn't have that huge like dual 6-member ring type of system. We just have a 5-member ring with the sulfur on it.
Yeah. No, yeah, it's a bit smaller, and I think are most of these are not sulfonamides, which is cool. You often see that a lot with antibacterial type medications. Those SO, for lack of, I'll just say SO bonds, right?
Mm-hmm.
I don't think we have any in these structures. No sulfonamides.
Well, we could keep going through some more of these. So we do
kind of maybe just
where like several more.
This one's quite large. Is this one? Oh, okay. Yeah.
Oh, so which one did you want to look at?
I think the first one that you pulled up. One back, yeah. They're all massive. They're all just huge, which makes sense. They're all massive ligands.
Yeah, that third one seemed even larger. This one, and it kind of like has a Y shape to it here, which is very interesting. I don't know if that makes it better or worse, but yeah, that kind of 3-fold. Oh god! And then what is this? Like a 1, 2, 3, 4, 5, 6, 7 weird 7-member ring thing here.
Yeah, this thing is huge. This is huge. This is a massive compound. This is
Yeah.
huge. Which is why a lot of the first stage in drug discovery, I care about, does it bind, whether or not it gets, not that I don't care about whether or not it gets a biological target, but get passed to the next person that can help figure these things out, right? When you take this compound as a medication, will it get there? In my line of work, probably not.
So just to kind of highlight, this is technically the heaviest one. This has the ligands menu. I sorted by molecular weight, and this is molecular weight 572. Yep, so you can see 572.099.
Yeah, that's a great label. This is a large compound. I don't know if this will make it to our if we'll end up buying this one and sending it to the research group for biological testing, but that'll probably take probably at least another, I still have a few more calculations to do, a few more things to screen, probably another month and a half, maybe 2 months to select and purchase these compounds and send them for testing. But I don't know, it's like I wouldn't be surprised if we ended up choosing some compounds that are this big, 500 AMU. That co-crystallized ligand's large, and I wouldn't be super surprised. It's a big binding pocket, right? It has a lot of room to work with, as we talked about. It's a lot of room to work with.
And I just overlaid in purple. This is the smallest one, and that one has a molecular weight of 376. So yeah, this might be getting a bit jumbled for people online, but just to compare the the heaviest and the lightest in the data set. Technically, there are some more with more atoms than the heaviest one, but they're pretty close in weight.
Yeah, I was almost trying to look at the smallest one and figure out, well, with it overlaid, it's a little harder to see. But well, I was trying to say, when we had them overlaid, when we had the smallest one overlaid the biggest one, I was trying to figure out why this molecule is so small, and I kind of am figuring it out now. It's just a ring at one side, right? Ring on the other side, this dual ring system. Then it just said not that it's an alkyl group, but there's no rings in the middle. It's a long linker region, right? It's just like acts kind of like a long linker region. Whereas before, in those bigger structures, there were ring systems inside the linker region that are linking these two binding sites together, right?
Yeah.
There's no rings in this one.
What I was alluding to earlier, right? It's almost like we have, two different druggable pockets that we're working together. And yeah,
I mean, it really
definitely showing that.
It displays exactly what you said really eloquently. Yeah. 2 rings in each binding site, then this linker region that's basically just a straight chain. There's no cyclized groups in there.
I have in my hand the builder tool, and there were a few areas where we maybe wanted to kind of pick up some hydrogen bonds. So Asher, let's say we wanted to get an interaction with this residue.
Well, I would say up here on this ring system.
Okay, sure.
You have this acceptor over here. What if you put an alcohol group here, OH, then maybe it'll hydrogen bond over here. If you put an alcohol, it's probably either, I mean, it might not work exactly, but it would either be this position or this position. This position, it might clash, but we could try it over here. Put an alcohol there instead, OH group.
So let's do that. So we'll do that, and then we'll just have the maybe, and I'm gonna go ahead and save. And I'll do add new ligand, so we'll kind of see them overlaid. Cool. All right. So is that about what you were talking about?
That's exactly what I was thinking. Yeah, if you put an alcohol there, you might, hydrogen bond over here. What other types of things do we see? Take a look. Because you could do alcohol there. You could probably do in an amine group. You could do You could do NH. It also might hydrogen bonds there. I'm also thinking. I mean, I was before thinking about the. We're talking about that aromatic residue. I remember. Somewhere in this region, there was an aromatic residue. The pi we were talking about. I'm kind of surprised. Yeah, this one right here. I'm surprised this residue down here, this phenylalanine. maybe pi with something in the ring system up here. Maybe the geometry is just not exactly. Yeah, it's not exactly right for that.
What about this on the other side? This little oxygen. We could like add a nitrogen right there.
Yeah, you could. This is the you're talking about this backbone one? Yeah, you're the backbone one. Yeah.
Yeah, here I just made the update. If you can see that, and yeah, it looks like I picked up a hydrogen bond. Hey, that's something.
Hey, well done. Look at you. Well done.
Should
Excellent work. That's pretty good.
name this molecule the Steve compound when it goes to clinic. Honestly, this one doesn't seem like that bad of a compound, and I kind of want to replace that alcohol with another nitrogen, but again, like I don't know, like my medchem intuition is based on spending many hours in VR with scientists.
Yeah, you have
but
intuition.
not
It's perfect.
formally having a PhD.
Well, it doesn't matter.
Yeah.
It doesn't matter. Yeah, you can put a nitrogen there. Yeah, put an amine there, and then H group. Yeah, why not? Instead of an alcohol, might pick up. Because are these auto minimizing when you these aren't like minimizing, are they? The structures when you make the changes.
No,
Yeah.
not in this
So I
version.
mean, no. So I mean that would take a lot. I think that would take a lot of power if it was auto minimizing the structure. We're just like kind of slapping them in there, right?
Yep, exactly. But I mean, it's based on these decent bond angles and bond lengths.
Yeah,
So
that's true.
it's not terrible in terms of slapping them in there. But
Right.
yeah, we're just putting it based on. Cool. Well, I think this is great. You should definitely order this compound and then add those nitrogens and see if it improves it.
Yeah,
really
when I send it to
appreciate your research.
when I send it to the research group, I'll say this is Steve. This compound just called Steve. That's it.
Yeah, Asher, by the way, if you log in tomorrow, and you should be able to download the smile string of the new Ligand and whatnot as well.
Got it.
So
That's
if you
funny.
really want to send it off, you know.
I mean, to be honest, I'm only gonna I can search for it and see if it's available on MolPort. I mean, it might be. If I'll take a look and see if it's available. With the way you analogged it, it might, because you put a nitrogen on this position, right? Is that what you did? You just put a and that was a hydrogen before. That was a hydrogen, probably.
Exactly. Yeah, they were all just hydrogens.
All right, I could search it on MolPort and see if it's there. I'll let you know.
Did, nitrogens on both sides. That's
Perfect.
my special move here.
I love it.
Yeah. But yeah, I mean, don't also waste your money and stuff if you don't think it's possible. So.
Well, no, a lot of the MolPort stuff I usually look through a database called Specs. Well, MolPort sells a bunch of different. They have different suppliers. One of them is Specs, and I like Specs because they're all $22 for 10 milligrams for all their samples. So if it's a $22 cost sample, I don't mind. No big deal.
I'll pay for that. It's easy.
Yeah, no big exactly.
Fantastic. Well, yeah, I hope that you get some good hits out of your physical screen when you do order the compounds.
Usually like these types of things, they have been working pretty well for me. So like I've done this with other proteins, carbonic anhydrase, and it worked pretty well. And I have a bunch of other collaborations, and usually you get a few hits. Like usually it works pretty well. Like usually out of a batch of, let's say we buy 50 molecules, like 20 of them binds, right? So it's not too bad.
Nice. Yeah. The more I look at this, the more I'm like, you know what? This has potential. Like I want to see this research carried out. Any closing remarks here, Asher?
Not necessarily. I mean, what we could do is the closing remarks is in a few months when we actually have data, we can look at some of the molecules that actually bind. We can kind of reconvene again and look at what did bind, and that'll be kind of interesting to kind of take the viewers along the ride for the project, right? How does this go from idea and theory to a publication or an actual drug, right?
Fantastic. I'm looking forward to that. Well, thanks so much for hopping in and showing me these compounds. Best of luck with the cancer research. Let's cure cancer, survivor over here with my, just light skin cancer. But yeah, it affects so many people around the world.
Yeah,
so really glad for people like you trying to help with different treatments.
course. Well, thank you so much, and I'll see you next time, Steve. Bye-bye.
Fantastic. All right. Thanks, Asher.